Now that we know that electrons are found orbiting around the nucleus of an atom, we can start to describe an address where we can find these electrons. But before we can do that, because what we're going to end up building is called the electron configuration. Before we can do that, we have to understand how these energy states even exist. So if you can imagine a ladder, and on this ladder, we have a couple of rungs of the ladder. So here's rung 1, and here's rung 2. And if you've ever climbed a ladder, you probably realize that your foot can land on either rung 1 or rung 2 or rung 3. And it can travel between these rungs, but it cannot exist between the rungs. And when I'm stepping down, I can start from 3 and I can go to 2, or I can start from 3 and I can go to 1, but I can't just exist in the middle. Well, that's the way that electrons are organized as well. They exist in these quantized states, like rungs of a ladder, or like the candy coating on a piece of candy. So what we have are these principal energy levels, and these energy levels are like these shells or rungs of the ladder, and you can step between, but you can't exist between for a long period of time. Now, an electron in the n=1 principal energy level is going to exist in what's called an s orbital. That s orbital is a spherical shape. Now, every one of our principal energy levels has what is called an s orbital. So that spherical candy coating. The n=2 principal energy level also has what is called a p orbital subshell. There are 3 p orbitals in a p subshell. Now, every orbital can contain a maximum of 2 electrons, but when you have what's called a degenerate orbital, so orbitals like the p orbitals are called degenerate, they are the same energy. Every orbital is going to get 1 electron before any orbital gets 2. So I figured before we start with electron configurations, I'm going to show you how these things build. So when we have something like oxygen has 8 protons. So it has 8 protons, that is its atomic number, and a ground state oxygen will also have 8 electrons. So we can build and fill those electrons. Now we're going to start with the n=1 principal energy level. And I'm going to show my electrons by creating single-headed arrows. So here I have 2 electrons in this s shell. This is 1s2. And that's shown like this. So we have this superscript of a 2 to show how many electrons are there. Now I have 8 electrons, I've used 2. I'm going to come up here to this second principal energy level, and I'm going to put 2 electrons here in the s subshell because it's a little bit lower than my p subshells. So now I've used 4 electrons. Now I have 4 electrons left, and this is what I was talking about. Everybody is going to get 1 before anyone gets 2. So because the p orbitals are called degenerate orbitals, all 3 of these p orbitals have the exact same energy. They only differ in their position. Everyone's going to get 1 electron before anyone gets 2. So I would show that, although I would show that as 2p4, this is what would be called the orbital diagram. And I would show that with boxes like this. So this is called the orbital diagram. It's a graphical representation of where you can find electrons. This is what's called the electron configuration. Now, I think I said that the s orbitals are spherical shaped. So you can imagine like a round candy that's been dipped in chocolate, and that first layer of chocolate is your first principal energy level. Then you go back in and you dip it again. And when you dip it again, you get that second principal energy level. And not only do you get an s, but you get 3 p orbitals. Now, those p orbitals, like I said, are orbitals of direction. And I'm awful at drawing, but I'm going to try. So we have a px orbital that would look like this. We have a py orbital that would look like this. And then we have a pz orbital that would look like this. So they're kind of dumbbell shaped, and they all have a node right in the center. That node is a place where you're not going to find electrons. But the important part for you is what order do they come in, and how do I write an electron configuration? Well, the first principal energy level, is important to know, only has an s orbital. The second principal energy level not only has an s subshell, so an s orbital, but also a p subshell, so 3 p orbitals. The third principal energy level not only has that s and that p, it also has what's called a d principal energy level, and that, or a d subshell. And that d subshell has 5 orbitals to it. Now, you don't have to memorize this because this is on the periodic table. Now, on the periodic table, we have what are called the main group elements, and that's comprised of these 2 and these 6 columns. The columns are also called groups. So here are my main group elements, and then these are my transition elements. Now, how does that relate to our electron configurations? Well, as you can see on this particular periodic table, we have the s group here, the p group is here, and then we have the d group. So as I move across the rows on the periodic table, I'm filling up my electron configuration. So the electron configuration for hydrogen is 1s1. It's in the first period or row. So we only have the first principal energy level. And when we only have one electron, it's only going to exist in that 1s orbital, so it's 1s1. Moving all the way over here to helium, helium's electron configuration would then be 1s2. We then move down a row on the periodic table, which is kind of like adding a candy coating or stepping up on that rung of the ladder. And then the full electron configuration for lithium would then be 1s2, showing that we have filled that orbital, and then 2s1. Beryllium would be 2s2. So beryllium's electron configuration would then be 1s2, 2s2. Boron, we would add to the p shell. We've now filled up our s orbital. Remember that any orbital can hold a maximum of 2 electrons, and the s orbital is only 1 orbital. So now we're moving over to the p subshell that has 3 orbitals. So boron would start filling the p shell. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Now these are not the electron configurations here. What I'm showing is how it's filling. So the full electron configuration for, say, carbon would be 1s2, 2s2, 2p2. So you go through and you fill what you can and then show what's not quite full yet. Until we get to the end, we aren't full on that principal energy level. So these are what are called the noble gases. That's what this column group or family is called. And these have a full valence. So the p shell is full here with 2p6. I step down to the next period or row, and then I would start filling the third principal energy level. So all principal energy levels have an s orbital, so that's what I fill first. And then I come over here, and then I'm going to fill the p orbital. So argon's principal energy level would then be 1s2, 2s2, 2p6, 3s2, 3p6. So then I step down another principal energy level, or another rung on the ladder, and then I can start filling the s orbital. Now here is where it gets tricky, right here, because this is the 3D orbital. If we draw an energy diagram, then we have our 1s here, we have our 2s here, and 2p isn't far from 2s. So we have, our rungs here. And then we have our 3s, and we have our 3p, which isn't far from 3s. Then we have our 4s. But our 3D is just ever so slightly higher in energy than our 4s. And because it's just, and I probably drew it wrong, but because it's just ever so slightly different, when we drop down to the fourth principal energy level, the fourth period on the periodic table, this is actually 3D that we're filling. And this is 3D 1, 2, 3, etc. So you don't have to remember that there are 5 d orbitals. All you have to do is count on the periodic table that there are 10 columns here, and know that that's where the d orbitals are. So the electron configuration, say for vanadium, we would start at the top, 1s2, 2s2, 2p6, 3s2, 3p6. And I know that those are full because it's in the 4th row. And then 4s2, 3d3. So that would be the electron configuration for something like vanadium. Now we do have some special cases. And what I want to point out first before we really get to those special cases, this electron configuration table is in the lesson. It's also in the ebook. So you are welcome to it. You are welcome to print it, view it, whatever you need to do. Now, we do have some special cases where we have a half full S and a totally full D, or a half full S and a half full D. And those special cases are right here, and I just want to call your attention to them briefly. So what happens is one of those S electrons gets promoted. And when that S electron gets promoted, there's just this special stability state. And because of that special stability state, there are some electron configurations that they need to be remembered, basically. So these are the ones that need to be remembered, but most specifically, something like chromium, for example, the full electron configuration for chromium, starting at the first row, so 1s2, and then bring it down to row 2, and then row 3, and then row 4. Now I'm in row 4, and it's 1, 2, 3, 4 over, but I do have that special stability state. So I'm going to have 1 electron in the 4s and 5 electrons in the 3d. Whenever you can make that leap for that special stability state, do so. And the ones that you need to know, I know I highlighted an awful lot here, but chromium and molybdenum for sure, copper, silver, and palladium for sure, maybe ruthenium and rhodium. You shouldn't need to know these two for my class, but the ones that I have circled for sure. So that is building a full electron configuration. Now I would like to point out in the first column, which is also known as a group or family, there is 1 electron in that s orbital. In the second column, group or family, there are 2 electrons in that s orbital. And over here, notice the patterns that we start to form. The periodic table was organized in a specific way on purpose. So those are our electron configurations. Now we also have what are called abbreviated electron configurations. We abbreviate an electron configuration by using the electron configuration of the nearest noble gas, or the noble gas that we just passed. So let's do that. So this was 1s, this was 2s, this was 3p, and that should have been a 2p, and that should have been a 6. So if I'm looking at, let's see, 4s1, 3d5, so I'm looking at chromium here. When I was building this electron configuration, I went through argon. So I went across and across and down and across until I got through argon, and then I started building 4s1, 4s2. So this business here, we can abbreviate that as argon and then build from there. Now that only works with these elements. They're the only ones you can put in square brackets. Those are called your abbreviated electron configurations. Now there is a little bit of quantum mechanics that you are supposed to understand according to the Kansas Board of Regents. So we're going to talk a little bit about what are called quantum numbers. These quantum numbers are numbers that indicate not only the principal energy level, as you can see here, the n value being your principal energy level, but also what are called the L values. Now these are angular momentum quantum numbers. So what we have, let's see if I can take a quick screenshot of it. So what we have when L equals 0, so L is the angular momentum. When L equals 0, that is an s orbital. So all principal energy levels have the possibility of having an s orbital. When L equals 1, we have what is called a p orbital subshell, or a p subshell. When L is 2, we have the d subshell. And when L is 3, we have what is called the F subshell. And I'm not even going to begin to try to draw that one for you, but the F subshell has 7 orbitals in it for a total of 14 electrons possible to be built there. And you can see that in the actinide and lanthanide series on the periodic table there at the very bottom. So that is quantum mechanics in a nutshell and how to build electron configurations. These are the kinds of things that require practice, but you'll get it.